Okay, so dear colleagues, let us start our BIMS integrable seminar for winter season. And our first speaker for after the break is Yuancheng Xie from Shenzhen about commutative ring of differential operators with more than three generators. So Yuancheng, please, you are welcome.
Okay, thank you. First, I would like to thank their invitation from Andre and also Ivan, and also thanks for their introduction. So today I'm going to talk about a story that connects commutative rings of differential operators and algebra curves. Okay, so first let's begin with like a classical problem. So assume we have two differential operators. L1 and L2, so of order n and m respectively, and we assume n and m there are co-prime for just a simplicity. So in linear algebra, when we have like two matrices, we want to consider when the two matrices they commute with each other, and as like differential operators, they are infinite dimensional generalization of matrices. It's natural to consider when these two differential operators they commute with each other. Okay. So in 1920s, Burchnall and Chaundy, so they consider this question when L1 and L2 they commute with each other. And they obtained their following very beautiful result says that if L1 and L2 they commute with each other, that means like their commutator becomes zero. Then there's a polynomial, okay, in two variables, alpha and beta, such that QL1 and L2 equals zero. Since L1 and L2 they commute with each other, so there's no problem of this order. Which one comes first? Okay, so that immediately connects the series of linear differential operators with their series of algebra curves. Actually, this alpha and beta are nothing but the spectra of the spectra of L1 and L2. That means we have L1 per psi equals alpha per psi and L2 per psi equals beta per psi. So they have to, when they commute, they have to have like common eigenvectors, but they can have like different eigenvalues. Okay. So, but unfortunately, this beautiful theory was forgotten for almost like 30 years, 40 years, until like in 1970s. And then Krichever rediscovered it and found their connection with the theory of integrable system. So now let's consider the simplest case that when L1 has order 2 and L2 has order 3. So we have two differential operators have this following form. And then since the order of these two differential operators, they're quite low, so we can calculate the commutator of these differential operators like directly. And we obtain a second order differential equation, external differential operator, sorry. So it's a second order differential operator, and we set this to be zero, and that will give us three equations. And in this two differential operator, we have like three unknown functions. And now we have like three equations, okay? So if we eliminate V0 and V1 from these three equations, and we will obtain an equation for K, for U0. And you will see that, so if you do this calculation, you can see that it's nothing but a stationary KdV equation. So that means like this is exactly the part that doesn't have like ut. So if I set like this equals ut, then that's exactly like a KdV equation, classical KdV equation. Okay. So so when people begin to consider like you can clearly see that in the theory of Burchnall and Chaundy, and we have like two differential operators, they commute, and then we have one equation in two variables that will define an algebra curve. So it's a plane algebra curve. And it's very natural to consider algebra curve defined like in more general projective space. Um, for example, like in P3, we can also define some algebra curve by certain equations. Actually, like at last, we found like in 1980s, there are some mathematicians already begin to consider this kind of questions. But we didn't when we were working on this problem, we didn't know that. Okay. Actually, we begin to work on this problem from a very different perspective. And now we begin to we begin the story that how we arrived at this one. So my talk will be divided like into three parts. The first part I will give a general background on integrable system and like you know I will prepare some background for common understanding of this problem. And the second part, I will introduce like what kind of a problem that leads us to consider or construct like these differential operators. I will so the second part will be about the problem and also the strategy, how we solve this problem. Okay. And the third part, I will introduce some like of our main results. So this talk is based on a joint work with Yuji Kodama. So first, let me use a few slides to introduce like the KP hierarchy. So many of you might be already like very familiar with this theory, but I want to set some stage like which like give some background like how we consider this kind of a problem. So KP equation is a partial differential equation, a nonlinear partial differential equation, like has their following form. So here we consider, we consider like this partial derivative is with respect to like T1, T2, and T3. So that means like partial one is partial and partial T1, and partial two is partial and partial T2. And we consider u is a function that depending on like infinite many time variables. And if we so u depends on like t, and the t is a set of time variables t1, t2, t3, etc. Okay. So in this equation, if we set like t1 equals x, t2 equals y, and t3 equals t, then this is the classical KP equation. So this equation is remarkable as it admits like infinite many symmetries, and each symmetry, continuous symmetry, is parameterized by like one of these time variables. And if we consider all these symmetries together, then we will get what's called like KP hierarchy. And KP equation is the first member of this hierarchy. Okay. It's this system is is interesting in many perspectives, and it's also like kind of universal. So this is a kind of a universal hierarchy in the sense that many other integrable systems it can be obtained as reduction of this system. It's actually this system is associated with a general linear group of infinite dimensional general linear group, and many other hierarchies are sub-hierarchy corresponds to subgroups of GL infinity, so they can be obtained as a reduction from this one. For example, if U doesn't depend on T, we said like T1 equals X, T2 equals Y, and T3 equals T. Okay. So if U doesn't depend on Y, and then we can get rid of this term. So this term will become zero. And we will just be left with this one. And this is nothing but a KdV hierarchy, KdV equation. Okay. Okay, so if there is any questions, please just stop me. Okay. So according to the theory of Sartre, there is actually a tau function in this form. So we can write u of t as a second derivative, of log tau. And if we don't know anything about this tau function, then this is nothing but a change of dependent variables. Okay. So so here there's a characterization of tau function. So tau function, it was characterized by the following condition. So if we expand any function f of t in terms of this so-called Schur polynomial, and then we will get some kind of coefficients. And this is a tau function of Kp hierarchy if and only if C lambda satisfies all their Plucker relations. Okay. So let me use a few words to explain what some of this terminology and the functions here. So first, let me explain this. Okay, as lambda of t. So this is the so-called Schur polynomial, and it can be constructed in this way. Okay, so first we need to define what's called elementary Schur polynomial. It has a generating series, looks like this. So we just take an exponential summation Tm Zm, and then we expand this and reorganize this in terms of like the power of the n, and then the coefficients are Pn of t. So for example, like there are a few terms that we can write down. So P1t is nothing but t, and P2t, and then it's nothing but T1 square plus T2, etc. Okay, so if we set like a degree of T1 to be 1, degree of T2 to be 2, and then these are always like homogeneous polynomials. And if we put all these elementary Schur polynomial into a matrices like this, so lambda is a partition. That means it's a sequence of positive integers. Okay. So we have like lambda 1 is bigger than lambda 2 is bigger than lambda 3, etc. So they are integers, and in the end, they will be 0. Okay. And then if we put them inside these matrices, we will get like what's called the Schur polynomial. So this polynomial actually exists in mathematics already for more than 100 years. So this is basis. So this is if we just take this Tn to be 1 over n, and then x1 to the n plus x2 to the n plus etc. Okay, if we imagine that there are infinite many like variables x1, x2, xn, so each of these ti is a symmetric power sum function. So this is a symmetric function. And then if we plug in this ti into inside here, then this is the Schur polynomial like in the series of symmetric functions. So this is exactly the same one. So it's not a symmetric function in terms of t, but it's a symmetric function in terms of x. So since each of these ti, they are symmetrical functions, and their function of symmetrical functions are also symmetrical functions. And we know that their power sum function, they are generators for their symmetrical functions of ring. And then we use them to get additive basis for their symmetrical functions. And we know that these Schur polynomials, they have like extremely nice properties. For example, if we use T1, T2, T3 as variables, then S lambda will be a basis for this formal power series ring. Okay, so that means what? That means actually any formal power series can be expanded in terms of S lambda of T. So this is a basis. So that means any formal power series can have such kind of expansion. So you can just think of this as some kind of expansion, like so compare this with Taylor expansion. It's just here we use the a different basis, but it's also like a polynomial. Here, like we have multi variables. Okay, that's all. So compare this with Taylor expansion. Now we explained what's S lambda of t. Let me explain also like a Plucker relations. Okay, so these are relations that come from an embedding of if I have a Grassmannian, and then I can embed it to a projective space. For example, we have like the simplest one, Grassmannian to 4, and then we can embed it into a projective space. And Grassmannian to 4 means like we consider two planes inside a four-dimensional space. Okay, so these two planes we can we can write it as a 2x4 matrices. A11, A12, A13, A14. And each of these rows is a vector in this plane. And if these two rows, they are independent, then they will expand. They will expand a plane. So this so other planes in C4. So this is the represent a plane in C4 can be expressed in this way. And then we know that if we change their basis, and we wouldn't change this plane, so that means we have a GL2 act on the left on this 2x4 matrices. Okay, and use this action of GL4, we can actually simplify this matrices generically. We can simplify it, so we can normalize the first 2x2 entries to be identity matrix, and we are left with 4 independent variables. And this embedding happens in this way. We take other minors, 2x2 minors of this 2x4 matrices. So let me write their minors as data 1, 2. That means I take their first and their second column, and the data 1, 3, their first and their third column, data 1, 4, and the data 2, 3, data 2, 4. And the data 3, 4. So from this 2x4 matrices, we can cook up like six minors. And if we use a GL2 act on the left on these minors, then that's just a scaling. So these six numbers actually live in projective space. So that means we will map this into projective 5 space. Okay, and we just said that. So GL24 generically it's dimension 4. So it's dimension 4. And we embed a dimension 4 manifold variety into a dimension 5 space. So that means like the image had to satisfy some equation. And then this equation is called the Plucker relation. For example, here the equation reads in the following way: data 1, 2 times data 3, 4 minus data 1, 3 data 2, 4 plus data 1, 4, data 2, 3 equals 0. So all these Plucker relations are these such kind of equations that they are quadratic. But these coefficients must satisfy all kinds of different Plucker relations. Okay. So in some sense, we transformed like a partial differential equation into use nice basis and then transformed into a sequence of equations for these coefficients. That's all. Okay, so even now we have this, then we need to find some kind of coefficients that satisfy all these kinds of Plucker relations. And we know that the Plucker relations comes from their embedding from a Grassmannian to the projective space. Okay, so a natural place to find this coefficients which satisfies other Plucker relations is from the Grassmannian. So Sartre gives the following way to construct this Grassmannian. We consider the formal you know the Laurentius ring of Z. Z is just a dumb variable. So later we will see that this corresponds to a spectral variable. And then this space can be decomposed into two parts. So we allow that there are the inverse parts. So it just have a polynomial part. So it has a polynomial part. So but for z to the n, we allow all their formal part series. Okay, so this space will be decomposed into direct sum of these two parts. And the difference of these two parts is that, so this is separable. So this space is separable, and this space is not. So it's a separable. That means like this space, we can find a basis for this space. So what's our universal Grassmannian? Our universal Grassmannian manifold is other subspace of V that is comparable with V empty, with V empty. So that means we take other subspace of V empty, and we compare with V empty. We compare with V empty, and we want it to be, you know, just a very like V empty. So this can be characterized in the following ways. We consider other subspace of V such that this projection map, it has like a finite dimensional kernel and two kernel. So since this space is separable, just like a V empty, and then we can take a basis of this space U, subspace U, and if we take a basis of this subspace U, and then we can expand. So we can do Taylor expansion or Fourier expansion, like whichever way you view this. And then there's some kind of coefficients. We put these coefficients into a giant matrices. So this is a matrices that has size like Z by N. Z is other integers. N is N is other natural numbers. And so for example, like this is the first function in this basis, and we expand it. We expand it in terms of z to the i's, and we have the coefficients, and then we put their coefficient in the first column. Okay, and then we have another function like in this basis, and then we expand in terms of Taylor series, and then we put their coefficients into their second column, etc. And we consider those subspace that has a basis, have their following form. So all the above are zeros, and we have 1-on-1s here, and we have a something non-trivial here, and here can be trivial or non-trivial. Okay. So this is the universal Grassmannian. And if we embed this into some giant projected space like P infinity, and all their minor, if it's satisfy all the Plucker relations. Okay. Now, this is like a very general way to construct the solutions for KP, but it's too general to be we can make any use of. So now let me give you like another way to construct some very concrete solutions for this KP hierarchy. In 1970s or at the beginning of the 1980s, people found the following thing. So if we take any function fi of t, and then it satisfies their diffusion hierarchy or heat hierarchy. It depends on how you call it, because when n equals to 2, so this is the heat equation. And then if fi of t satisfies this simple heat hierarchy, and then we take the Wronskian of these functions. So it looks like this, and then it turns out that this will automatically give you a tau function for KP hierarchy. Okay. For example, so the elementary short polynomial that we introduced before, so this satisfies the heat hierarchy. We can check this like very quickly. For example, so this generating series, it's obvious that if we take a derivative with respect to Tm, That's the same thing as we take a derivative with respect to t1 and then multiply by m. So m times, okay. And so if we apply this on the right, we'll see that Pn of t actually satisfies the heat hierarchy. And then so this is nothing but the formula that we wrote before. So this is actually a Wronskian formula. So that means S lambda of t itself actually gives a tau function for Kp hierarchy. So this is a tau function for Kp hierarchy. And then we actually we just used this as a building block to build all the other tau functions. And another fundamental set of solutions of the heat hierarchy is just a generating series of this elementary Schur polynomial. So we randomly choose any like m variables, kappa 1, kappa 2, kappa m, and then we use this as a basis. So this obviously satisfies other heat hierarchy. And since heat hierarchy are a set of linear differential equations, we can just do some linear combination. And then it also satisfies the other heat hierarchy. And we use all these fi's, fi of t, and we write down its Wronskian, and then that will give us tau functions for Kp hierarchy. And such kind of tau functions will be just some linear combination of exponential functions. And we call such a function, such solutions, soliton solutions to Kp hierarchy. And here is the connection between like these two constructions. Okay, we talked about like universal Grassmannian manifold, and we talked about another way to construct the soliton solutions for Kp hierarchy. And here is their connection, how we connect these two together. So we can we need to find out what kind of this solution defines. So this kind of solution defines which kind of subspace of this V or point, which point in the universal Grassmannian. It turns out that if we expand, if we take a basis for this one, and then so it's nothing but this guy. So you can see here that when k is bigger than n, so it's z to the negative k. Okay, it's z to the negative k. That means nothing but something like this. So after like n, so this goes to like a positive infinity. This goes to negative infinity, and after like the height n, and then this is identity matrices. Okay, there's nothing here, so this is 0. This is 0. And then there's something non-trivial here. And as you can see that since this is identity matrices, so there's only like finite many columns that's non-trivial here. So we can take the determinants of the minors of these matrices B. That's allowed. Okay, and then we expand this in terms of z to the I, and their coefficients will just give us a point in the universal Grassmannian manifold. So this is their second class of solutions of Kp called the soliton solutions. And in 1970s, so Novikov school, like in particular Krichever, actually proposed a general construction for quasi-periodic solutions for Kp hierarchy. So it's expressed in terms of Riemann theta function, which if you don't know, that's also fine. If you know, that's good. If you don't know, that's also fine, because we are not going to use this. We will reformulate this story, and in terms of universal Grassmannian. So as you can see that the Riemann theta function actually took the place of tau function exactly, because so the general solution of Kp is this, and then is 2 times partial 1 square log of tau. And then this constant, you can just, it's nothing but like a theta function times some kind of quadratic form, Ti, Tj, and then Qij, you will get this constant. In any case, so this theta function is some in some sense, it's a tau function for KP hierarchy. And here, let me say a few words. So this D is a vector that depends on like Riemann constant. So K is a Riemann constant vector. And all these constant C, omega J's, they're obtained from their second abelian differentials. So that's some kind of meromorphic differentials defined on some algebra curves. Okay. So Siegel-Wilson actually reformulates this story like in the following way. So we take the following set of data. So first, C tilde is a Riemann surface, smooth Riemann surface. And on this smooth Riemann surface, we take a smooth point on this Riemann surface. And around this point, we take a local coordinate. So let me mark this. So the smooth Riemann surface. Okay, so P infinity is a smooth point. And then we take Z as the local coordinates around the P infinity. And we take L as a line bundle of degree G. I will explain more explicitly what they are in concrete examples. And this phi is a section of L. Okay. So if we have something like this, we can get a point in the universal Grassmannian. So we just take other functions on these Riemann surfaces, and we allow it has like arbitrary order of poles at P infinity. So we write it in this way. So that's a section of this line bundle, but we allow arbitrary order of poles at infinity. Okay. So this can be like 1, 2, 3, and etc. Anything. And each time we take, we take 1, 2, 3, etc. Then this is an infinite dimensional space that will give us a point in UGM. So you just need to use this phi to write all these things in terms of like expand so get a basis for U, and then expand in terms of do the Taylor expansion, and then get their coefficients. You will get a point in UGM. Okay. So this map will call like a Krichever map.
Yuancheng, sorry. Here's Sasha. Can I interrupt you for a moment?
Yeah.
I just want to make a remark that Ziegler and Wilson used another version of universal Sato Grassmannian based on L2 spaces on the circle. And Sato,
yes.
And you used another version, the purely algebraic version offered by Sato.
Right.
So just a remark. So because the question is, and maybe you will comment it somehow, how these two Grassmannians are related.
Yeah. So it's so how these two Grassmannians are related. That's a good question, and thanks for asking. So first, yes, you're right. So Siegel-Wilson actually used more analytic. So there's more analytical ways. So there's more analytical flavor. You just consider like L2 space, on a circle, and this circle is around like Z, okay, around this P infinity point, and then we consider functions which is holomorphic either inside of the disk S1 or outside of the disk S1. Okay, and Satu is a more algebraic way. So this is more algebraic way. So we consider that like the empty it's always separable, and the V naught we allow it to be inseparable. So the relation is actually, Siegel-Wilson is inside Sato theory. Because for this L2, we actually allow, either inside and outside, so they are both separable. So we have a disk, and we have a P infinity, and around this P infinity, we have a local coordinates, and use these local coordinates, we take a unit circle S1, Okay. And then we consider like other functions, L2 space, like on this L1. And then this will give us like a decomposition of these functions in this space. So half of each will be analytic inside the disk. And another half of each, we imagine that, this is a disk on some Riemann surfaces. And actually, so Sartre formulates not just this one space. He gives a sequence of spaces that you can suitable to study like KP hierarchy. So this is the biggest one, and also there's a smallest one that you just consider, these matrices that has finite many non-trivial entries, and that will give you all the rational solutions of KP hierarchy. So that answers your question.
Well, yes, okay, I understand what I was talking about, but it was just a remark that there are two different versions of Grassmannian, and the main for solutions of the KP hierarchy appearing from the curve, there are no questions. But if you take some generic solution, then some question will appear. So, but maybe we can skip this question until the end.
Okay. Thank you. So here, in my, you're right about that. And in my construction, you will see that other solutions that we will consider will be, will fall into like both the definition of Sartre and the definition of Siegel-Wilson. Okay. So yes, that's a tricky question. That which space, which one that you consider. Okay, now let's consider let's consider a simplistic example. Okay, what we are talking about here. So let's consider a KdV equation that's it has the following standard form. And then you will assume that this KdV equation has their following solutions. U x of xt, it has their following like wave solution. And then we just plug this into their differential equation. We'll get their first line. Okay. And here, if we choose A and C properly, for example, we choose A equals like 2/3 of C, and then we will this will simplify a little bit. So that means like this term and that term, they will cancel. And we will get this one. There are only two terms left. Okay. That's this one. And then if we multiply f sub x on both sides of the, we can integrate it once and get this equation. After we integrate it once, we get this equation, and we can multiply f sub x on both sides of this equation and integrate it again. Then we will get this equation. Okay. So this one is nothing but normal form. So where's Strauss normal form? Of elliptical curve. So that means like so this equation is satisfied by f equals where's Strauss p function. So we can. So that means Weier's stress p function is actually give us a solution for KdV equation, and that's the quasi-periodic solution that we saw that constructed by Krichever. Okay, it's this one. Now, if we take some kind of a limit, so we rewrite this elliptical function in terms of Jacobi elliptical function, and we take some kind of a limit. We let E2 goes to E3. So EI is the, this elliptical function is defined by y squared equals 4x to the third minus g2x minus g3. So the right-hand side is a, degree 3 polynomial. So we can decomposed it into, it has three roots. So the three roots, we write it as E1, E2, and E3. Okay. And if we degenerate this algebraic curve by letting E2 goes to E3, so then these two roots will come together, and we actually get a rational curve, and then our solution, elliptical function, will degenerate to trigonometric functions. And the trigonometric functions, of course, you can write it in terms of like exponential functions, and then that gives us a soliton solution. And if we degenerate further by let C goes to 0, okay? If we let C goes to 0, and then this elliptical curve will degenerate further to a cusp. So this is a rational. And then this corresponds to a cusp. And the elliptical function will also degenerate to just rational functions. So this corresponds to the rational or polynomial solutions of KP. For example, like the simplest one we mentioned before is this tau function is this. Tau function is s lambda of t. This is a polynomial. And then if we take the log of tau and then take a twice derivative with respect to t1, we will get a rational function. And so this one is a special case. Okay. So let's finish the first part. Now let's come to the second part. So what kind of problems that Yuji and I were interested in? We can see clearly that we have three sets of different solutions. So the top one is the quasi-periodic solution. And it corresponds to some smooth algebraic curve. And if we degenerate this algebraic curve, we will get the soliton solutions. And if we degenerate the curve further, we will get rational solutions. Okay, but the soliton solutions we constructed either by finite dimensional Grassmannian, just like in this way. It's very different from this construction of algebro-geometric solutions. And then that propose us to study the following question. So actually we have a classification of soliton solutions of KP. And we're wondering whether all these soliton solutions, they actually correspond to some algebraic curves, whether all of them comes from some, maybe singular algebraic curves. But what are these algebraic curves? Okay, so this is the question. What are the algebraic curves that's associated with the soliton solutions of the KP? So in 1970s, we already have some examples. For example, we can degenerate the algebraic curve associated with the KdV, that's hyperelliptical curve, degenerate to some rational curves, and then we obtain like soliton solutions. Okay, so already in 1970s, people wondering, like in general, these curves will be just some rational curve. And with double singular point, but somehow like other than hyperelliptical curve, we didn't have like many other examples. So we want to, so in some sense we want to reconstruct the algebraic curve from these soliton solutions. Okay, and here is how we do it. Since we can embed like all their soliton solutions and also their quasi-periodic solutions into the universal Grassmannian, we'll use the universal Grassmannian as a main tool to make this study. So first, we'll embed this data from soliton solutions into universal Grassmannian. Okay. And we know that if we have a smooth algebraic curve, we can have like Krichever map to map this data from a smooth algebraic curve into Grassmannian. universal Grassmannian. But when we embed this, soliton data into the universal Grassmannian, we know that, a priori, we know that it corresponds to some singular curve. And for singular curve, there is no Krichever map. But tentatively, we use a Krichever map to point back to get some data. And this data is, we have to make a guess. So this data, we have to make a guess. And whether this guess is correct or not, we don't know, okay? And we have to check it. So how we check it? We obtained some singular algebra curve and a point and all this data. We want to know whether, really like this is meaningful. Then we do some kind of deformation. We have a singular curve, then we do a deformation, make it smooth. And on this smooth curve, we have this Krichever map. We can map it into the universal Grassmannian. And now if we can degenerate this from this smooth algebra curve, we can degenerate it into the soliton solutions. And then this side will be also valid. Okay. So this is the logic.
Sorry, I'd like to comment it again.
Okay.
Just sounds a little bit confusing that you said that there are no Krichever map for singular curves, because it exists.
Yeah,
maybe you mentioned here that you just want to have a non-singular curve for your construction. So the question, maybe the correct question is how to construct a smooth curve whose degenerations leads to a soliton solution. Because by a point of universal Grassmannian, you can always reconstruct this data with singular curve, and the Krichever map exists for singular curve as well.
Yes, you're right. So if we have singular curves, and then you can study like not line bundles, or you can study shapes and all this general abstract stuff, and then cook a map here, right?
Yes.
But now what we want is we begin with some like a very singular data, and then we want like an inverse map.
Yes, but so as far as I understood, it can be always reconstructed. So I mean, by your point of Grassmannian, you can always reconstruct something. Of course, it will be not a smooth curve.
Right. But whether this one is unique or not, and there are other things like how you construct. I mean, so in some sense, this is more or less like a Torelli problem,
Yeah, in a sense, well, in a sense, you can do it like in Lasse's article, for example. It's a generic stuff.
Yes, but I want to do it. But here the point is, I want to do it very concretely.
Okay. So that is
okay.
Another comment, just to avoid some misunderstanding. So as far as I understood your problem, you want to deform the singular curve.
Yes, exactly. I want
something smooth and concrete. Okay.
Right. I want to find the smooth curve which degenerates. You're exactly right. We want to find a smooth curve which have like a smooth quasi-periodic solutions, smooth algebra curve, and we degenerate to their solutions that are soliton solutions. Okay. So, and in general, yes. So you will have begin with a singular curve and a singular data here. We also have a map here, but now we want to do it very concretely, like not abstractly. Here we have a point. We want to find the explicit point here. Okay, that's the point. Thank you.
Just a specification of the question. Yeah. Okay.
Yeah. Thank you for clarifying. Yes, if I'm happy that you clarified. So okay, let's see how concrete we can do. Okay, otherwise, as you can see, it's not meaningful. So let me justify by how concrete we can do this. Let's consider hyperelliptical curve. Okay, we want to explicit as explicit as this much. So there's a line bundle. A line bundle is a degree G line bundle is nothing but we take G points on this on the algebra curve that's defined by this equation. So we write it like a P1, P2, PG. And each of these PIs, it's a point on this curve. That means I can take X equals CI square and Y. So it's on this curve, means it satisfies this equation. So I take it to be this one. And then you plug this into this equation, it has to satisfy this equation, okay? And the basis, then I want a basis from this, functions, algebraic functions that are constructed from this algebra curve. That so what's the function of this, divisors? So at these divisors, I allow like a simple pole at each of these points, nothing, so nowhere else. And I allow like a arbitrary order of poles at infinity. Okay, so my P infinity is there infinite points, and there's only one infinite point here. So let me give a basis for explicit basis for this for this subspace. So first, I know that if I define this kind of equation, then I have all my xy, they only have poles at infinity. Okay, so they must be part of this data. And then any x to the j's, y to the k's will be such a function. But I don't need like y to the second, because y squared can be replaced by a polynomial of x. Okay, so here k is only 0 or 1. And x to the j can be anything. So we have this. But other than that, we also have a need to construct some functions which have a simple poles at these points. But we know that, if we have a hyperelliptic curve, then it's a double cover of CP1. So we have CP1 here. It's a double cover of CP1, 2 to 1. And each point, it has like 2 inverse images. And we allow that it has a pole at PI, but it has like 2 inverse images. We need to eliminate we need to make, the other point is not the pole of this one. So we construct the functions hi tilde of z. And then at last, we use this hi tilde of z and all the such kind of polynomials as a basis for u. Okay. So a very explicit basis. And then we can expand, as I said before, we can expand all this in terms of their power of z to the i's, and then there's a coefficient, and these coefficients we can embed into universal Grossmannian. Okay, that's a point in universal Grossmannian. Now we make this degeneration. So we make lambda I square, lambda g plus I square to go to go to the same number, kappa I square, which is not 0, because 0 is already like roots of this. And then the degenerate curve will look like this. Of course, like this basis is a point in universal Grossmannian. This basis will also degenerate. And after we checked, like you do some observation, we see that this basis can give us after the degeneration, it will degenerate to this point. So this is 1 and something, 1 something, 1 something. It's still quite complicated, but it gives us the data for soliton solutions. Recall that the soliton solutions that we constructed before is it has like 2 parts of this data. So we just need some kind of spectral parameter, kappa j, and the other data is matrices, finite dimensional matrices. Okay, so here this is their finite dimensional matrices, and their kappa j is nothing but this kappa i's. So we have G of these kappa i's, and we have a matrix like this. So this is still quite complicated. If we want to go back from this to some algebra curves and to line bundles, to sections of line bundles, is still quite complicated. Now let's do some further. Let's do some further degeneration. Let's say I goes to infinity. Then this matrix becomes extremely simple. 1 minus 1, 1 minus data like only this matrix, and also kappa 1, kappa 2, kappa g. So the remarkable thing is we only need this matrix and this spectral data to construct this degenerate algebraic curve. To construct this degenerate algebra curve. Okay, so we can begin from this matrix and this to construct this degenerate algebra curve and then construct this quasi-periodic solutions in general. So that's our that's a model for our theory. So now we want to so do something more general. We observe that
we have 5 minutes left.
Okay, I will use this 5 minutes to get to the point, hopefully. So this is the tooth roots of unity. Okay. Now we cook up like a more general matrices that we just use like the k's root, l's root of unity. And as these matrices, that means like we have 1, omega square, omega, etc., omega l-1, and then we repeat this pattern because KdV, the case of KdV tells us like that's a good matrices. And from these matrices and from this spectral data, so we reverse all this process, we can construct a singular algebra curve, which is defined in the following way. Okay, we have like a 2 by L matrices, and from this 2 by L matrices, we take all the 2 by 2 minors of this 2 by L matrices. And these 2 by 2 minors, we set all of them to be 0. So in general, there are lots of equations, and there are only like x and y1, y2, yl-1 on n variables, but there are lots of equations. But remarkably, if we set all these 2 by 2 minors to be 0, that defines a singular algebra curve. And we know that this singular algebra curve is not plane curve, because this singular algebra curve has like a very, has a singularity that you couldn't possibly put it on the plane. So the simplest case is a 3, 4, 5 curve. So it has a singularity looks like this. Okay, so it's this curve will just first across itself, and then across itself again, like at the same point, but in another direction. You have to put it into. So this crossing is just like in 3-dimensional space, R3. We look at the axis of this 3-dimensional space. So it comes in 3 different directions. That kind of a singularity. And you couldn't put this kind of singularity on the plane. So that means it's intrinsically, it's not a plane curve. And we have to use why we have to use L of these variables as generators, and all these curves we can actually use a numerical semigroup to parameterize it. Okay, so we construct an algebra curve. Now the next question is this algebra curve a spectral curve for some, this is their degeneration. Okay, we can degenerate, we can smooth it. I will skip this part. So you just need to expand all these lambda j's to be different, then you will get a smooth curve. So now the question is whether we can realize this algebra curve as spectral curve or some differential operators. And if we can, then what are these differential operators? Okay, so at last we found if we begin with a pseudo differential operator and from Gelfand decay, and then that means L to the L's is a differential operator. If we begin with a differential operator like this, and then we take other B's, that's L to the alpha, L to the beta, we take the differential part. And then we make a linear combination of these operators, we get L alpha. And we can prove that all these operators, L alpha, they commute with each other. Okay. And their algebra curve, their spectral curve is exactly their spectral curve that we defined by all their 2x2 minors of these 2 by L matrices. And if we take their simplest one, 3, 4, 5 curve. And then we will have three different differential operators. They commute with each other, and then they satisfy like three algebraic equations. Okay. So I will stop here. Thank you.
Okay, thank you for your talk. Yeah, so questions or comments?
So Yuancheng, just one question. So far, could you obtain all soliton solutions defined above in such a way, or it's only
no, that's too ambitious. We actually you can see that we actually chopped a very small like piece from these soliton solutions because our so in general you want a general matrices A, right?
Yeah.
But we made this observation. We understand like how KDV works, and then we generalized this KDV construction to get from the decay. But a general one that corresponds to like arbitrary matrices. We don't know like how still we don't know how to construct this algebra curve from this degenerate ones. No, we choose like very special ones. We know how to do it. It's just like this special matrices is nothing but as I said, it's 1 omega square and omega L minus 1, and then we repeat this pattern like several times. And we actually can do a little bit better because these curves are labeled by some numerical semigroup, and we can do a little bit better. We can generalize this to some all these ones that are parameterized by some numerical semigroup looks like this. But actually, even here, we have like this problem that we couldn't solve. So we can construct a singular algebra curve, but we don't know how to do deformation for this algebra curve to make it smooth.
So do you have a deformation only for hyperelliptic?
No, we for more general. So we have a deformation for example,
for all of that type, yeah, which
yes, for all that type. So it's actually this deformation is quite simple. So for singular curve, we have a g of x is nothing but x times f of x. So for example, if we have two by two blocks, so this is just a y1, f, and the g is x times f, and that's nothing but a hyperelliptic curve. Okay. And then if we expand it into this, so g singular curve is still like g of x equals x times f of x. And now you want to make it smooth. You just need to make the factors, the roots of f is different from the roots, other roots of g. So even none of them are the same, then it's smooth. It's smooth.
Okay, thank you.
Yeah,
so
but in general, that's still far from complete.
Yeah. Could you please again show the slide with this Grassmannian description of soliton solutions?
Soliton solutions. Okay. Let me go back here. Yes. So this is the general theorem that makes sure how you can construct it, and the basis we choose is this one. Okay.
Yes. This one. So as far as I understood, in this Grassmannian, so this is a generic Grassmannian description. I mean, this theorem by Nakayashiki, Kadam, and Hiu, right?
Yeah.
So any soliton solution can be given by such a point, right?
Yes, we can prove it by some kind of representation theory. Yes.
Yeah. But with arbitrary Aij and Kj, right?
What?
And with arbitrary constants Aij.
Yeah, arbitrary constant Aij belongs to some Grassmannian. So it's a point from a Grassmannian. So that means arbitrary Aij, that is n by m matrices that has rank n.
Yeah, I understand. And kappa j are also arbitrary, right?
Kappa j arbitrary, also arbitrary.
Okay. So it seems to me, well, okay. I have asked you before, but the same question. this point looks perfectly for applying the Wilson's formula to reconstruct anything. And have you tried them to reconstruct the curves, etc.? Maybe
the construct for general ones?
Yes.
We tried. We tried very hard, but you know, even there seems we don't know many algebra curves. I mean, you know, the algebra curves, it has a moduli, but anything you can write down, it's very special already. So
but this curve will be always for a specific type. I mean, it will be quite easy. I mean, this curve will be either with cuspidal singularity or with nodal singularity only.
That's not true. For example, the curve that we construct, it's not like a nodal singularity. It's soliton solutions, but it's not nodal singularity.
No. I mean, under nodal singularity, I mean exactly what in generalized sense. Exactly what you write down. It's again predicted by Wilson. But by that reason, I asked you about that. Maybe this Wilson formula will help to.
I will. Right. Then I will talk with you like more. What do you mean by Wilson's formula?
Well, there are formula expressing tau function, the curve, and even maybe and anything else. So maybe just using them, you can just write down the curve and then try to deform it.
That will be I mean, if there is such a formula, then that will be like very nice.
Okay, just a question, an offer.
It
seems to me very natural.
Okay, but I will send you email to ask for the you know, exact reference. I will be very happy to see, you know.
Okay.
And also the other thing is like, you know, this their construction of this differential operator. It's also like you know, very rare because even in the theory of Burchnall and Chaundy, people know like you know, degree 2, degree 3, degree 2, degree 5 maybe. And the degree 3, degree 4, that's already like a paper in 1990s. Like you know, except a full paper calculates like when like L3 and L4 commute. So that's already like a paper. But here we give like you know, a bunch of like you can literally L can be arbitrary integer.
Yes. Well, again, I think that Wilson's formula fits well into this construction of differential operators because he related the question of constructing differential operators of rank 1 with rational or trigonometric coefficients by singular curve. So as far as I remember, these operators can be reconstructed exactly by his formula. But I mean, if you know this psi function or the tau function given by this formula, and in your way, for this point of the Grassmannian, you can reconstruct the tau function by either by Sato formula or by Wilson's formula. Then I believe you can easily construct differential operators. I mean, what is easily? If you have a computer, you can always do it because you know the coefficients.
Okay.
But if you want something, some beautiful formula like this one, yes, maybe work on this.
Okay, then we definitely we need to chat and then
yes,
to see and we can get more.
Yes. This is just the ideas, natural questions from me.
Right. But that's indeed like quite interesting for me, you know.
Thank you.
I have a little question. So you considered the KDV specialization of KP.
Yeah.
And the soliton solutions correspond to these hyperelliptic functions.
Yes.
And what about more general case? Is it possible to associate soliton solutions to theta functions, quasi-periodic theta functions, which are not, I mean, the spectral curve here it's even not algebraic, yes, because
it's algebraic, and it's more general than hyperelliptic. What I mean is, you know, this is a 2 by L, and then you take other. So you take other 2 by 2 minors of this, and this is a generalization for KDV. When you know L equals 1. Let me see. When L equals when L equals 2, I think. So that means this is like a simplest case. You know, it's like this L equals to 2, then you will have y1, fx, gx, and then you just have one equation. So this is y1 squared equals fx times gx. And this is exactly what we obtained here, right?
Yes.
So now you generalize this, like you have a 2 by L matrices, and your equation is like you know you need to choose different columns. That like you know in general you don't need that many equations, but from algebra geometry you need, because you need to, you know, you want to have like if you just let me write like simple ones. For example, y1, y2, and then this is gx, this is fx, and then you have y1, y2, right? Now you will have 3 equations. 3 equations in projective space P3. And you know that like in P3, I only need 2 equations. I only need 2 equations to get a curve. And the third equation is redundant, but it's not, because if you use 2 equations, you will get like you know, you will get like a curve with many components. And the third equation will get rid of the extra components, and will decrease this just into like one irreducible pieces.
I see.
Okay.
So it and the curve is not algebraic here, no? In general,
it's algebraic. It's just I mean, all these equations are still like algebraic equations.
Hmm.
So for example, we construct like you know, L1, L2, L3. So this corresponds to x, y1, and y2. So still, you know, these 3 differential operators, they commute with each other. And we know the theory from Burchnall and Chaundy, if 2 differential operators commute with each other, they have to satisfy some algebraic equations. Okay, and that's still valid. Now we have 3 differential operators, they commute with each other. And then when you show each 2 they commute, they will give a algebraic equation. So you need to put all these algebraic equations together. That's still like an algebra curve.
So the Riemann surface is has 3 sheets. Is that correct? Here in
yes, exactly. That's 3 sheets. So that means this simplest one will give you 2 genus 2 solutions of Boussinesq. This is actually, as far as we know, not very well known. Because you know, before people construct like people when people study like Boussinesq, so what they do is they just consider like a y to the third, the simplest one, y to the third, x to the fourth, and if this one is smooth, it's genus 3. And this is exactly what I'm talking about. Like the singularity is very different. So in 3-dimensional space, if you want to resolve this singularity, you just need to shift this axis along one of these axes. For example, shift it here, and then you will have like 2 double points.
Yes.
So that's why like genus 2. Okay, but if in their plane you have 3 lines intersect together, and then you move it a little bit, you will always get like 3 double points.
Yes, yes, yes. I agree, of course. But the example I was thinking about was a Riemann surface, I mean, which is singular at infinity in the sense that there is a branch point at infinity and even infinite branch point.
Yeah.
Order. So does it exist?
Oh, that to be honest, I don't know.
I have a concrete example, but I don't know how to formulate it as tau function.
So maybe we can find some time, like, to look into more closely. To be honest, I did not consider these questions before.
Okay, thank you. Thank you.
Thank you.
Okay, so thanks the speaker again.
Okay, thank you all of you to come to this talk. Yeah, and also for good questions and comments. Thank you.